Okay, class. So there were a couple of things I was hoping to go over um, from the lecture slides that we did. So primarily this idea of linear independence. So again, I think we had two vectors. So let's write those out. So it was v, and again you can see the notation I'm using. You got to put that arrow above that v because we can't really bold, on a piece of paper. So here 1 and 2, and then u was 1 and -1. Okay, and so these apparently, we want to know, are these two, so are v and u linearly independent? All right. And so then again, it comes down to that rule that we were discussing where, this is on page 7 of your notes, where can we solve, so can we solve C1 times V plus C2 times U equals the 0 vector. Okay, I'll put an arrow on that because that's the 0 vector. All right, so let's see if we can rewrite this out. So what that says is, if we bring this to the other side, so we have C1V equals negative C2U, right? And that comes from, again, the little blip above section 4 on page 7. And so then we want to divide both sides by C1, and we get V is equal to negative C2 over C1U. Right? Okay, so let's plug in the numbers there, and what we'll get is, are there constants C1 and C2 such that 1, 2 is equal to negative C2 over C1 times U, which is 1 and -1. Okay. Is this possible? All right. So we can also do this another way if we'd like, but we can just write this out. So again, using that scalar multiplication, we can see is 1 equal to negative C2 over C1, right? And then we also have 2 is then equal to negative C2 over C1 times -1, which means 2 is equal to C2 over C1. Okay? Or C2 over C1 equals 2. So you can see here automatically, like this statement and this statement are not, you can't satisfy both of those at the same time. All right, so if we multiply both sides by -1, we get C2 over C1 equals 2, and here we get C2 over C1 equals negative 1. All right. So if you can't solve this system out, then you've got what's called linear independence. And that's another way of saying V1 and VU, they span all of R2, right? So we have the span of V and U is equal to R2. Okay. So that was something I wanted to cover. I'm assuming everyone had an okay time with the vector addition subtraction, because that's just basic elementary arithmetic restricted by the positions on the vectors. Let's move on to matrices real quick, because I also wanted to cover that. So, all right, so again, if we've got, let's say we've got, I'll make it simple. Let's say it's a 2 by 2 matrix. So we have A1, 1 times x1 plus A2, 2 times x2 is equal to B1. And then we have A2, 1, x1 plus I made a mistake here. That should be 1, 2. A2, 2, x2 is equal to B2. I'll write this out. So you've got, if you just, look at one of those equations, that's just a linear equation. You've got another one here that's also a linear equation. These entries, depending on what B2 is, A21 and A22 are going to be different than they are up here. Unless, of course, B1 and B2 are equal to each other, but then there might be some other combinations depending on x1, x2. Anyways, we don't need to think that far down the rabbit hole. So here, we can essentially, what we want to do is we're going to want to factor these x's out of that and create their own vector, because you can see here x1 and x2 are the same, but a11, a12, a21, and a22, the different constants, they don't have to be equal to each other. All right. So how can we write this out in a way that will we could put it into a matrix form? And the way we do that is you write it out as such, where you're going to have a11 up here, a21 in this corner, a12, and a22. And you're going to multiply that by x1 and x2. And that's going to be equal to this vector b1 and b2. So can we show that? Of course. So when we multiply these out, again, don't forget how you do your vector multiplication. It's this entry here in the first part of the vector times that one, plus this one times that one. It's the dot product, as we said. So we basically did a reverse dot product to decompose this system of linear equations into a matrix form. All right, so if I factor this out, or I'm sorry, if I multiply this through, what I'll get then is I'll get a1 times x1, or I'm sorry, a11 times x1, this times that, plus this times that, plus a12 times x2 equals this entry up here, equals b1. And then down below, you multiply across, and again, it's first elements multiplied with each other and added. So a21 times x1 plus a22 times x2 is equal to B2. And there you have it. This is identical with what we wrote, what we started off with up here. All right, those are equivalent. Okay. And I think the next video is going to go over the operations on the matrices. So I'll probably end there. Just one last bit of notation. So we can actually write this using vector notation. So here you can see this is a vector, but this is a matrix. And typically the way we write matrices is we write them with capital letters and we put an arrow above them. So that's, noticed, since it's capitalized, it's matrix A. And then this vector here, we usually would call that a vector X. And then we make that equal to this vector B. Just like that. All right. Okay, hopefully this is helpful. And, you know, especially with the linear independence, you know, maybe we can do another linear independence question here. All right. So let's see. Let me see if I can use some of the numbers that we did right. So here I think we had the following. So we proved that V and U are independent. So that means we should be able to solve any system. So here, let's go with, let's say we have A1 times 1, 2. Again, this is vector V plus A2 times 1, negative 1 is equal to, so now we have to think of just a random B vector anywhere in R2. The trivial one is the origin. So if you put 0, 0, all you need to do is say, all right, A1 is equal to A2 is equal to 0. But we want something a little less trivial than that. How about 3, 3? Right, so that's a 45-degree line starting at the origin, terminating at point 3, 3. Can we write a linear combination of these so that we're going to have, we're going to use the addition rule, and we're going to stretch them out by a certain amount, A1 and A2, where if we add them together, we nail this point here, right? That's kind of the idea here, is you're given this vector and you're given that vector. You're going to use them to kind of formulate an ingredient, or I'm sorry, formulate like some kind of a recipe, so that you end up with this vector here through the process of vector addition. And these A1 and A2, all they do is they stretch that vector out, or they shrink it in case it becomes negative. All right, so then all we really have to do is write out the algebraic system, right? And so we just multiply across. You can see here this is going to be A1 plus A2 is equal to 3. And then the bottom one is 2 times A1 minus A2 is also equal to 3. So since they're both equal to each other, what we can do is set them equal to each other, and we have A1 plus A2 is equal to 2A1 minus A2. Okay? And let's solve for one of these. So let's solve for A1. So it's going to be A1 minus 2 times A1 is equal to negative A2 minus A2. Right? So this will be negative A1 equals negative 2 times A2. Or in other words, if we divide both sides by negative 2, right, we get A2 is equal to 1/2 A1. It's just that Gaussian elimination. And now we can take, we can take this value or this expression and substitute it into either one of these expressions up here. Let's just choose the first one. So A1 plus a2, but we know that a2 is 1/2 a1, is equal to 3. And now we can solve for a1. So this is 3/2 a1 is equal to 3. Just multiply by the reciprocal, and you get a1 is equal to 2. We substitute that back into here, and we get that a2 is equal to 1. And simple as that. So let's see, if we plug these values into this expression, do we actually get what we want? So let's do that. All right, so a1 is 2, so it's going to be 2 times this vector 1, 2, plus a2, which is just 1, -1. Does that give us this target, 3, 3? So 2 times 1 is 2, plus 1 is 3. 2 times 2 is 4, minus 1 is 3. And I think we're good. All right. What does that look like? What does that look like on paper? I'm going to do my best to graph this, but don't hold me to anything. All right. This is going to be not very pretty. I'm going to tell you that now. Let me make some room here on my table. Okay, so we need two vectors here. We have the vector 1 and 2. So that's, let's say this is 1, 1, 2, 3, 4, 5, 2, 3, 4, 5, 6. So we need the vector 1, 2. That's 1, 2. That'll be this point here. Use different colors. That'll probably be helpful. All right, so this is the vector 1, 2. And then we've got this other vector 1, -1. So we're going to need to go across the origin. There, there. This is already off the page. That's all right. Okay, so 1, -1 is 1 towards the right, -1 down. So we're going to have this vector here. And what did we do? We multiplied this first one by 2. So we have to double the length. So it's going to go to 2 and 4, which is way up here, right? So let's make that with a with this color here. So we're going to go up this way out to this point here. Right? So that's 2 times 1, 2. And then we're just going to add this vector here. So this one goes down 45 degrees. So it's going to hit, when we move this vector, when we add it up to that point there, it's going to go down this way. So it's going to look like that. Okay? And the idea here is what is this vector here that we just created? Well, look at it. 1, 2, 3, 1, 2, 3. That's exactly what we wanted to build. And so you can see that just using these two vectors in some sort of linear combination with each other, we can hit any point on this plot anywhere, as long as these two vectors are linearly independent. Okay. All right. I'll stop the video there, and then if you have any questions, feel free to email. All right. See you in the next one.